So we are on to a slightly more complicated example than the circle one that we had done earlier. But notice again we have the sine and the cosine function here. So this is probably going to wind up being, an ellipse or a circle. Let's figure out which one. And in order to do that, we want to utilize the fact that cosine squared t plus sine squared t is equal to 1. And in order to do that, I'm actually going to solve this one for cosine and this one for sine, and then we'll square both of them. Go ahead and do that. So we'd have to, for this one, we'd have to add 2 to each side first. So we have x plus 2 is equal to cosine of t times 4, right? It was 4 cosine t. And to finish this, let's just divide by 4. So we have x over 2, or x plus 2 over 4 is equal to cosine t. And let's do the same thing here. Let's solve this one for sine of t. And so if we did that, we'd have y minus 1 divided by 2 is equal to sine of t. And now, if we were to, again, use the fact that cosine squared t, and I'm going to write this in a different color this time, cosine squared t plus sine squared t is equal to 1. And let me not forget my t's here too. Cosine squared t, sine squared t. There we go. Next step will be to actually square cosine. Okay, and we know that cosine is x plus 2 over 4. And we know that sine is y minus 1 all over 2 squared. And this is equal to 1. And we could even rewrite this a little bit different. If we square the top, that's x plus 2 squared, and square the bottom, that's 4 squared down here. And then plus, again, square the numerator, and then square the denominator. And now this looks like an ellipse. This should be an ellipse with center minus 2 comma 1. So minus 2 comma 1. Here's the center of our ellipse. And so you can see here that under the x plus 2 squared, we have a 4 squared. So that means in the x direction, we should go out 4 units from the center. So 1, 2, 3, 4. So here's 1 point on our ellipse. And if we count 4 the other direction, 1, 2, 3, 4, that'd put us over here. So these are 2 ends of our ellipse. And then you notice that there's a 2 below the y term. So that means we're going to go up 2 units and down 2 units from the center. Okay, in the y direction. That's the key here. In the y direction. And so we're just going to connect these with an ellipse. My scaling's not perfect here, so this ellipse will probably look a little off, but let's go ahead and do that. There we go. Close enough. And then when you finish up a problem like this, it's also not a bad idea to check on the calculator. Okay? But we're actually not done, are we? We don't know what direction or where we started. Let's maybe think about that. If we were to look at t equals 0, then x would be what? 4 minus 2, so 2. Again, I'm just plugging in t equals 0 into the equation for x. And then if we let t equals 0 in this other equation, the equation for y, we just get 1. So we start at 2 comma 1. That's that happens to be right here, 2 comma 1. And then the period, right, would be 2 pi, and a quarter of the period would then be pi over 2. And I'm doing this just so that I can think about what 1/4 of a rotation would look like. Okay. So if we plug pi over 2 in, cosine of pi over 2 is 0. So we get 0 minus 2, so that's minus 2. And then over here for y, if we let t equal pi over 2 again, we need to think about what sine of pi over 2 is, and that is 1. Okay. That is 1. And so since we get 1, we have 1 plus 2 times 1, which is 3. So minus 2 comma 3 is where we end up after a quarter rotation. So that must mean that we are going clockwise again. This isn't always going to be the case, or we're going counterclockwise here. But it won't always be the case that we'll go counterclockwise. Sometimes this might be clockwise, and the only way to tell is to just plot where a quarter revolution would be, which is just the period divided by 4. And this is only on 0 to 2 pi, and so since the period was 2 pi, this only completes 1 revolution in those 2 pi radians. Let's see if there were anything else in the instructions here to do. Sketch the plane curve defined by the parametric equations by eliminating the parameter. So we have done that. Okay, we eliminated the parameter and we actually graphed it. Okay. And the equation where we've eliminated the parameter, I should point out, is right here. Okay. Standard form of an ellipse. On to our last example here. And again, we've seen a few different tricks, right? You can solve for t, substitute it into the other parametric equation. You can use the fact that sine squared t plus cosine squared t is equal to 1. Sometimes you have to use a trig identity. And here's even a different case. So this is one where you actually could solve for t if you choose to, or you could kind of make a clever substitution. Okay. So note, both of these actually have an e to the t, not just a t, an e to the t. So we could actually solve this one here for e to the t. So I'll give you e to the t is equal to y plus 8. And then we could note that, well, y is or not y, x is equal to the square root of e to the t plus 1, which implies that x is equal to the square root, and remember, e to the t is equal to y plus 8. So x is equal to the square root of y plus 8 plus 1. And so we've eliminated the parameter here. We could use this equation as it is. So this is a square root function, but you could imagine normally when we have a square root function, it's facing this way, right? Well, since this is x equals, our square root function is going to look more like this. But we'll see. Let's plot some actual points here. So first thing, let's try t equals 0. If we were to let t equals 0, we get x is equal to the square root of e to the 0 plus 1. And e to the 0 is actually just 1, so this is the square root of 1 plus 1, so this is 2. 2 for x. And a y is going to equal e to the 0 minus 8, which is 1 minus 8, which is negative 7. And now let's try maybe the end here. T equals the natural log of 8. What would it look like then? Okay. So if we let t equal, again, the natural log of 8, remember e and the natural log, those things undo each other. So if this is the x value, this is really just the square root of 8 plus 1. And if we were to look at y, it would be e to the natural log of 8 minus 8, which happens to be 8 minus 8, which is 0. So we have our 2 points here now. Let's go ahead and plot both of these. I'm going to get rid of this, though. It's messy work. All right, so 2 comma minus 7, that's where we're starting at, 2 comma minus 7. So 2 minus 7, that's somewhere down here, approximately. And then our other point, the square root of 8 plus 1 comma 0. Well, if you were to plug in the square root of 8 plus 1 into your calculator to get the decimal approximation, you'd find that it's pretty close to 3.8. So this point up here, the second point, should be somewhere in here. And if you wanted to, you could plot in a few more points, or you could even solve this thing for y if that helps, and is what you'd find is you would have a parabola. But let's just go ahead and connect our points here. And again, you might be wondering, well, what kind of curve? Well, this is a sideways, or a sideways square root function. Okay, so it should look something like this. And that doesn't look very curved, but I'm going to try and make this look a little better, even though this won't be perfect. And I suppose that's a little bit better. And we know that we are heading in this direction here. The only thing we need to change on our graph here is you may note that the t interval that we were given, it doesn't say t greater than or equal to 0, less than or equal to the natural log of 8. It says these are strict inequalities, strictly less than. Okay. So we shouldn't actually include our endpoints this time. They should actually be open circles, signifying that we don't actually have these points. So let's see if I can actually erase just the dot. I don't know if I can. It doesn't look like it. So, but it's what we'd want here. We'd want open circle there on the x-axis, and we'd want an open circle down here as well.